Hello friends, myself Dr. Nandakumar Raubawale from College of Engineering Ambazogai is going to deal with Applied Thermodynamics 1. This is our 22nd lecture on Applied Thermodynamics 1. In previous lecture we have discussed about efficiency of indirect contact heating cycle. Today we are discussing about use of Mollier chart, a small problem to find out the properties of steam using Mollier chart, and then we will study or we will discuss on a small numerical related to Rankine cycle. So now already I have explained you what this Mollier chart is and what we can do with Mollier chart. So even though today we will discuss about a small problem which will include to find out properties of steam. So already as we have discussed about the lines, what these lines represent on Mollier chart. So the vertical lines, all these vertical lines on Mollier chart represent constant entropy. All vertical lines on this Mollier chart represent entropy. So entropy is given along x-axis. So this is entropy 7.0, 7.5, 8.5 and so on. On x-axis entropy is given, whereas on y-axis so enthalpy in kilojoules per kg is given. So all vertical lines represent constant entropy lines, whereas all horizontal lines, say this is line, horizontal line, all horizontal lines represent constant enthalpy. Then we find here one curve. So this curve, a brown curve which is outside this, represents the dry saturated curve or saturated curve, means the property of steam on this curve is a dry saturated steam is available on this saturation curve. Then the lines which are having similar trend of this dry saturation curve, so you can find brown lines here in this yellow region. So these lines which are approximately parallel or having similar profile are known as dryness fraction curves. So these curves are known as dryness fraction curves. So these curves which are parallel to the saturation curve are known as dryness fraction curves. You can find here the dryness fraction as 0.7, 0.75, 0.8, 0.85, 0.9 and 0.95. So these are the curves which represent dryness fraction. So here in between this it is 0.94 and 0.93, 0.92, 0.91 and 0.9. So in this way these brown lines indicate the dryness fraction. Then after that there are certain lines which are known as constant pressure lines. You can see here this dark continuous line. So this dark continuous line is nothing but the line represent constant pressure line. So the point which is given here, 0.1, 0.1 is the constant pressure, 0.1 bar. So this line represent the constant pressure of 0.1 bar. And then after that next line, if we see here, this is 0.2 bar, then line here it is 0.3 bar, 0.4 bar, 0.5 bar, 0.75 bar, 1 bar, then 1.5 bar. So this is how these dark lines are representing constant pressure lines. Then after that we can find some dotted lines here. So these dotted lines which are parallel to the pressure lines are representing specific volume of steam, so constant specific lines. So you can find here AT is the specific volume of steam on this along this line. So along this line specific volume of steam is 80 meter cube per kg. So 80, 50, 30, 20, 10, 0.5, 2, 1, 0.5, 0.2, 0.1, 0.05. So all these are the constant specific lines, constant specific volume lines. Then after that So this yellow region below this saturation curve, so below this saturation curve, whatever area is there, this area, yellow area, is known as a wet steam region. And after that, whatever is the above this saturation curve or saturation line, this area above this is known as a superheated region. So steam above this is in superheated state, whereas below this curve it is wet state. So in this superheated region you find here yellow lines. So these yellow lines are known as constant temperature lines of superheated steam. So here this yellow line indicates the superheated temperature of 150 degrees Celsius. Here we can find superheated temperature of 100 degrees Celsius and so on. So here 50 degrees Celsius, 100 degrees Celsius and 150 degrees Celsius, 200 degrees Celsius. Now we'll take one example, and with the help of that example we will find out properties of steam. So let us consider the steam which is having pressure of 1.5 bar and temperature 150 degrees Celsius. So let us consider pressure of P is equal to 1.5 bar and temperature of steam T sup, temperature of superheated steam is 150 degrees Celsius, and you are asked to find out properties of steam. Find properties of steam. What are the properties of steam? So if we know temperature of steam, pressure of steam, then we can find out number one, enthalpy, specific enthalpy of steam, then specific entropy of steam, specific volume of steam. These things we can find out. So how to find out enthalpy, entropy and specific volume of steam? With the help of Mollier chart that we want to see. So coming back to the Mollier chart, pressure is 1.5 bar. So here the pressure lines we can find. So this is 0.1 bar, 0.2 bar, 0.3 bar, 0.4, 0.5, 0.75, 1 bar and 1.5 bar. So this line represents 1.5 bar pressure, and as we move along this line, so this line is going to cross this 150 degrees Celsius temperature here. So this is point, say P, point P, which is having pressure of 1.5 bar and temperature of superheated steam as 150 degrees Celsius. So first of all we want to find out enthalpy. So enthalpy at this line, constant enthalpy at this line is 2700 and here it is 2800. So if it is exactly at the center, it will be 2750. So it is above 2750 but closer to 2800, so it may be somewhere here. So if we take a horizontal line from starting from point P, so the enthalpy will be somewhere here. It may be 2780. So enthalpy at this point is, point P is 2750. So we can directly write here as enthalpy as 2750 kilojoules per kg of steam. Now entropy of steam, if we want to find out, so corresponding to point P, if we see corresponding to point P is exactly just closer to this. So we can come along this vertical line and here we can mark this point somewhere, just somewhere here. So it is 7.0, 7.1, 7.2, 7.3, 7.4, 7.5. 7.4 means 7.41. If we divide this into 5 divisions, 7.41. So entropy will be 7.41. So just higher than 4 means 7.41. 7.1 here we can write 7.2, 7.3, 7.4 and 7.5. Just this point P is on right hand side of this vertical line. So it is just on right hand side of 7.4, means instead of 7.4 we can write it as 7.41. So entropy we can write as 7.41 kilojoules per kg. So this is entropy. Then what about specific volume V? So if you want to find out specific volume at point P, so this dotted line represents specific volume and this dotted line represents specific volume. It is between these two dotted lines. Specific volume at this is 2, and here it is 1. It is between 2 and 1. So to which it is close. Whether it is exactly at the center, no. It may be, if it is here, it is at center. So it is just above center, means it is between 1 and 2. So it is 1.5. Before 1.5, it is before 1.5, means we can take it as approximately 1.4. So specific volume of steam at point P is between these 2 points. It is between 1.0 and 2.0. So if it is exactly at center, it can be written as 1.5, but it is before 1.5, means it is 1.4 we can write. So approximately we get specific volume as 1.4 meter cube per kg. 1.4 meter cube per kg. So these properties can also be obtained from steam table also. So how to obtain these properties from steam table, or by using the formulas that we see. So here, looking at this, enthalpy of superheated steam H soup can be calculated as HF plus HFG plus CPS T soup minus Ts. This is the formula to find out enthalpy of superheated steam. So this is enthalpy of superheated steam. Enthalpy of superheated steam. So from steam table, at pressure 1.5 bar, we can get all these values. So at pressure 1.5 bar, looking into the steam table, at 1.5 bar, HF is 467.08. So this is 467.08 plus HFG is 2226 triple 6.46 plus CPS is specific heat of steam is 2.1 into temperature of superheated steam is 150 degrees Celsius, which is known to us. 150 degrees Celsius. TS saturation temperature at 1.5 bar is 111.4. Close this. So if we calculate this, we will get this enthalpy as, we'll see here, 150 minus 111.4 into 2.1 plus 222 6.46 plus 467.08. This works out to be, with the help of calculator, if we find, this is 277.4.6. So these properties are taken at 1.5 bar. So if we see here, the value of enthalpy of superheated steam obtained by Mollier chart is 2750. Here it is 2774 kilojoules per kg. So if you do not remember this formula, directly value of enthalpy of superheated steam can be obtained from a Mollier chart. So similarly, entropy of superheated steam S soup is given by SF plus SFG plus CPS natural log T soup divided by TS. So again, from steam table, at pressure of 1.5 bar, we can take the values of entropy at pressure of 1.5 bar. Pressure of 1.5 bar, 1.433, 1.4339 plus 5.79 plus CPS is 2.1. Natural log. Temperature of superheated steam is 150 degrees Celsius, but this must be in degree Kelvin, plus 273. Temperature of saturated steam is 111.4 plus 273. So this must be in degree Kelvin. Temperature here must be in degree Kelvin. On simplification, we get entropy of steam, superheated steam as so 150 plus 273 divided by 1.4 plus 273 of natural log of this 1.4339 plus 5.79 plus 0.12 natural log of 150 plus 73 divided by 1.4 plus 273 7.25. This works out to be 7.2569 kilojoules per kg degree Kelvin. So here by graphical method we obtain it as 7.41. Here we obtain it as 7.25. So there will be minor difference between the values. The accuracy of the results obtained by using formula is more than the accuracy of results obtained from the graph Mollier chart. The specific volume V, specific volume of superheated steam is Vg into T sup divided by Ts. So Vg from steam table we have to take at 1.5 bar. At 1.5 bar Vg is equal to specific volume Vg is equal to 1.15933, which is 1.159 330 into temperature of superheated steam is again 150 plus 273 divided by 111.4 plus 273 close this bracket. So this will be 150 plus 273 divided by 111.4 plus 273, this is 273 plus 273 close this bracket into 1.15933. So this works out to be 1.27. Specific volume is 1.2757 meter cube per kg. So if we compare, this is approximately 1.3, this is 1.4, so there will be a difference between these values. So never these values will match because of observation errors or printing errors. So accuracy of graph may not be similar to the accuracy of results that we obtain by using formula. So here if you see, we can find out specific column of superheated steam, entropy of superheated steam, enthalpy of superheated steam using formula and steam table. Whereas here if we see, these values are directly obtained from Mollier chart. So one more example we will take for a wet steam. So in this case we will define this wet steam at some pressure. So for example, we'll take it as pressure of 5 bar, pressure of 5 bar and dryness fraction as 0.98. P is equal to 5 bar and dryness fraction X is equal to 0.98. Two things are required, at least two things. In previous case, pressure was known, temperature of superheated steam was known. Now here pressure and dryness fraction is known. So we can locate this point P or Q say at pressure of 5 bar and dryness fraction 0.98. So pressure of 5 bar, this pressure of 5 bar, this is 0.99, this is 0.98. So this point we mark as Q. So Q is at pressure of 5 bar line and dryness fraction as this is 1.99, this is 0.98. So if we see here, the second line dryness fraction is 0.98, so 0.95969798. So this point is Q. So corresponding to this point Q, we can find out enthalpy and entropy. So corresponding to this point Q, enthalpy will be 2700. Just 2700 in place of 2700, we can take it as 2705. So enthalpy is, enthalpy of wet steam H wet is 2705 kilojoules per kg. Now entropy of wet steam S wet at this point. So if we take entropy exactly at this point, it is between these 2 points, not at the center but just shifted towards left hand side. So exactly at this center, if we see here this point 6.5, 6.6, 6.7, just it is before 6.7, means it is 6.69. Entropy at this point is 6.7. Just less than 6.7 means we take as 6.65, approximately 6.65 or 6.66. So entropy will be less than 6.7, just less than 6.7. We take it as not 6.6, it will be 6.6, means here it is between 6.6 and 6.7, so we take it as 6.66. 6.66 is the entropy. The entropy we take it as 6.66 kilojoules per kg Kelvin. Now specific column, if we see the point Q is between these two dotted lines, it is very close to this dotted line away from this. So if we divide this region into equal parts, it will be divided into 3 equal parts approximately. So this is one part, 1/3. So this is 0.5 and this is 0.2. So 0.2 and 0.5, it is between 0.5 and 0.2, but it is closer to 0.5. So specific volume of wet steam, it is between 0.5 and 0.2, but it is very closer to 0.5. So if we divide this distance 0.5 to 0.2, 0.5 minus 0.2 gives us 0.3, and if we divide it into 3 parts, it is equal to 0.1. So that means 0.5 minus of 0.1 means specific volume will be approximately 0.4 meter cube per kg. Is it clear how we got this 0.4? So this distance between 0.5 and 0.2 is after subtraction 0.3. So we divided it into three parts. Why we divided into three parts? Because this distance of point Q from this dotted line, 0.5 dotted line, is very close compared to this dotted line of 0.2 meter cube per kg. So if we divide this distance into three equal parts, so this is one part, two part and third part. So only one part. From 0.5 one part is subtracted. One part is equal to 0.1. 0.5 minus 0.1, the specific volume at point Q is 0.4. So therefore we have written here as 0.4. 0.5 minus of this division of 0.1 is subtracted. So now enthalpy of wet steam, if we want to find out, enthalpy of wet steam is equal to HF plus X HFG. So at pressure of 5 bar, HF can be taken from steam table. At pressure of 5 bar, at pressure of 5 bar, enthalpy of liquid is, is temperature table. No, it is at 5 bar, HF is 641.21. 641.21 plus of dryness fraction is 0.98 plus into HFG value. HFG value at 5 bar is 2105. 2105.97. So now if we simplify this as 2105.97 into 0.98 plus of 641.21, so enthalpy will be, now if we see here, this will be 2705.06 kilojoules per kg. So if we see here, we have written as 2705, here 2705.06, so error is very less. So entropy of wet steam as wet is equal to X into Vg. So X is 0.98 into Vg specific, wrong. This is for specific volume. The entropy of wet steam is SF plus X SFG. So here SF value is taken from steam table at 5 bar. Again at 5 bar from steam table. Already you know how to see steam table. 5 bar SF is 1.8606. 1.8606 plus 0.98 into SFG is 4.96. 4.9606. On simplification, if we simplify this, we get it as 1.8606 plus of 0.98 into 4.9606. So this will be 6.72. So here this gives us 6.72 kilojoules per kg Kelvin. So if we see here, it is 6.72 and we obtained it as 6.66. So there is less difference. The specific volume of wet steam is X into Vg. So dryness fraction is 0.98 into Vg at pressure of 5 bar. At pressure of 5 bar, Vg is 0.37, 0.37489. So on simplification, we get this 0.98 into 0.37489, so 0.36 meter cube per kg. So this is the specific volume, here 0.4 and here 0.36. Approximately we obtained closer value. So it is always true that in graphical method we will get approximate results, not accurate results. So this is how the Mollier chart helps us to find out the properties of steam without knowing the formula or without referring the steam table. So here there are two methods. So by first method we can refer Mollier chart and we can find out properties of steam. In second method we can use steam table and we have to remember formula, and by remembering formula we can find out enthalpy, entropy and specific volume of steam. So if two things, at least two properties are known, such as pressure and dryness fraction uh, is known, pressure and temperature of superheated steam is known, pressure, enthalpy, any two properties if are known, rest of the properties can be obtained using Mollier chart. So any two properties, say for example we select one point somewhere here. Say for example we know enthalpy and entropy. So looking at this point, we know enthalpy, we know entropy, point is selected. So dryness fraction can be obtained, specific volume can be obtained, pressure can be obtained. So if we know any two properties of steam, rest of the properties can be obtained. So this is the uh, smartness of beauty of this Mollier chart, which helps us to find out quality of steam, or if quality or any two properties are known, rest of the properties of steam can be obtained with the help of Mollier chart. So next we'll be looking into a next thing, that is a small numerical which we want to solve today. One of the numerical is there. So let us see one of the problem on Rankine cycle. So this is the problem. A simple Rankine cycle works between pressure of 30 bar, and the condenser pressure as 0.04 bar. The initial condition of steam being dry saturated means dryness fraction of steam is equal to X is equal to 1, dry saturated. Calculate the cycle efficiency, work ratio, specific steam consumption. So these three things are to be calculated: cycle efficiency and work ratio and specific steam consumption. So how to find out these things, that we will see. So what is given first is pressure P is equal to 30 bar. P1, the higher pressure is given, pressure P2, condenser pressure is 0.04 bar. The condition of steam entering into the turbine is dry saturated steam. Then he is asking us to find out Rankine efficiency, work ratio and specific steam consumption. So now the TS diagram of a Rankine cycle is shown here like this. So we see here graph of this. So you can find here Rankine cycle like this. So now we can see here point A, B, C, D and E. So A to B is conversion of steam, liquid into dry saturated steam. From B to C it is expansion, and C to D it is condensation. D to E is pump work, and E to A is sensible heat addition. So now the efficiency is defined as net work divided by heat supplied. Net work divided by heat supplied in the sense work done by turbine minus work consumed by pump. So that gives us net work. So work produced minus work consumed. So here this is pump work, and here this is turbine work. Pump work and turbine work. So turbine is work is produced and this is work consumed. WT minus WP is net work. So net work divided by heat supplied. So heat supplied is from point E to A sensible heat, A to B it is latent heat supplied. So now very first we have to find out efficiency, means we must find out net work and then heat supplied. So to find out net work, in order to find out net work we must know turbine work and then pump work. So turbine work can be obtained by subtracting enthalpy at point B minus enthalpy at point A, HB minus HA. So enthalpy at point B is known, enthalpy at turbine work is HB minus HC. HB minus HC, enthalpy at point B minus enthalpy at point C. So enthalpy at point B can be obtained as HB is equal to HFB plus XB HFGB, but at point 1 the dryness fraction X is equal to 1. X is equal to 1. Here it is. Okay, no problem. So we will continue with this. So at point B, enthalpy at point B we can find out directly, but to find out enthalpy at point C we must know dryness fraction. At point B and dryness fraction is 1 because the steam entering into the turbine is dry saturated. So from point B to C the steam is expanded isentropically, therefore entropy at point B is equal to entropy at point C. So here entropy at point B is given by SFB plus SFG at point B. Then at point C entropy at point C is SFC XC into SFGC. C indicates the suffixes at point C, B indicates suffixes at point B. So pump is doing work from D to E. So pump work, so from this what we can find out is dryness fraction at point C, and from dryness fraction at point C enthalpy at C can be obtained. HC is equal to HFC plus XC HFGC. So this is enthalpy at point B is obtained. Here enthalpy at point C is obtained. So by knowing enthalpy at point B and enthalpy at point C, we can find out work done by turbine. So then afterwards we have to find out pump work. Pump work is given by, so net, to find out net work, turbine work minus pump work. So once we know turbine work, we can find out pump work. Pump work is given by specific volume VW into PD minus PE into 10 to the power of 5 divided by 1000. So where PD and PE are in bar. So if we substitute in bar, so work done is obtained by this formula. So once we know PD, we know PE, we know specific volume at point specific volume of liquid is also known. So everything can be obtained from steam table, and from this we can find out work done. So work done by pump is known. So by subtracting the pump work from the turbine work, we get net work, and this net work can be substituted. Then rest of the things is heat supplied. So how to find out heat supplied? So prior to that, PD is equal to P2. So PD means pressure, this is P2 and which is given as 0.04 bar, and P1 or PE, pressure at E, A and B is same. So this pressure is known as P1. So P1 is equal to 30 bar and P2 is equal to 0.04 bar. Then heat supplied. So from where to where heat is supplied? Heat supply starts at point E. Up to A it is sensible heat addition. A to B it is latent heat addition. So heat supplied is HB minus HE. If we know enthalpy at point B and enthalpy at point E, we can find out heat supplied. So HB can be obtained by this formula. But how to find out HE? HE, enthalpy at point E, is enthalpy at D plus pump work. So enthalpy at D plus pump work. Enthalpy at D can be obtained from steam table. HT is equal to HFC. So HD is equal to HFC or HFD. We can call it as HFD. So HD is nothing but HFD. So specific steam consumption is given by 3600 divided by net work done in kg per kilowatt hour. So now to start with solution, we must find out first of all the properties of steam from steam table. So what we must know is we have two pressures. One is pressure of 30 bar, another is pressure of 0.04 bar. Right, these two pressures will write down certain values from steam table. So already I have explained you how to see the steam table. Now from steam table we will collect some values here. So what values are required from steam table that we will see? Pressure table we will take. Here we take pressure P in bar. And second thing we take as so we take here SFG, entropy of steam, in kilojoules per kg Kelvin. So here we take SF in kilojoules per kg Kelvin, and we take here HFG in kilojoules per kg, and here we take HF in kilojoules per kg, and here we will take VG is required or VW is required. In this case we need VW. VG is not required. And here we need temperature of saturation, that is TS, in degree Celsius. So this is in meter cube per kg. So we have two pressures. Pressure 1 is 0.04 bar. 0.04 bar. At 0.04 bar, saturation temperature is 75.87. 75.87 degree Celsius, and specific volume is specific volume of liquid in steam table it is represented as VF, that is given as 0.001027. Then HF, enthalpy of steam, as 0.04 bar. It is at 0.04 bar. So these values are found. Just a minute. Point 0.04 bar. At pressure of 0.04 bar, the saturation temperature is 28.96 degree Celsius. Then VF is 0.01004 and HF is 121.44, HFG is 2432.93, then SF value is 0.4226 and SFG is 8.05, 8.0520. Again at another pressure 30 bar, at pressure of 30 bar, same values we will take from steam table at pressure of 30 bar. Saturation temperature is 200, temperature is 233.9 and VF is 0.001216, VHF 1008.41, then HFG is 1794.10, VSF is 2.6456, SFG is 3.5412. So these values are taken from steam table. Now coming back, what is to be done, what we have to find out at first, so that is to be decided. So this was our plan. So we started from here and we reached lastly at this point. So now what we have to find out, we have obtained all these values. So first of all, what we can find out is enthalpy at point A can be obtained, enthalpy at point B can be obtained, so enthalpy at point C cannot be obtained. So to obtain enthalpy at point C, we must know dryness fraction at point C. So HE, to know HE, we must know HD and pump work. To know pump work, we must know these values. So first, what has to be done at first? सबसे पहले क्या करना है? So to start with the solution, very first, we can find out HD value. So once we know HD value, then we can find out pump work. So if we know pump work HD value, we can find out HE. So after that, obtaining HE, we can find out HB also. So how to know HB? HB can be obtained for the enthalpy of dry saturated steam. So already HFG at point B is known, therefore we can find out HB. So we can find out heat supply. So pump work is known, heat supplied is known, then dryness fraction at point C can be obtained. After getting dryness fraction at point C, we can obtain enthalpy at point C. So once we know enthalpy at point C, enthalpy at point B, we can find out turbine work, then we can find out net work and then efficiency. So we'll start in reverse direction. So how to start in reverse direction, that we will discuss. Very first, we want to find out enthalpy at point D, say. So to find out enthalpy at point D, so here this is TS diagram. A, B, C, D, E. So first of all, we can find out enthalpy at D. So this is at pressure P2 and this is at pressure P1. P1 is equal to 30 bar and this is 0.04 bar. Now very easily we can find out enthalpy at point B, enthalpy at point D, because at point B steam is dry saturated and at point D the liquid is condensate is at saturated liquid. So enthalpy at, first we find out enthalpy at point B is equal to, we can call it as HB, and this is nothing but HF at point B plus HFG at point B. HFB, enthalpy at point B, HFB at pressure of 30 bar is known, so that is obtained in this table. HF at 30 bar, so HF at 30 bar is 1008.41. so here this is 1008.41 plus HFGB at point B pressure is 30, HFG at this pressure is 1794 1794.10. So if we add these two we will get enthalpy at point B 1008.41 plus of 1794.10. So this works out to be, enthalpy at point B is 2802.51 kilojoules per kg. So this is enthalpy at point B. So now enthalpy at point A can be obtained, enthalpy at point D can be obtained. So we find out enthalpy at point D. Enthalpy at point D is equal to HD. HD in the sense it is HFD, because condition of working substance at point D is liquid condensate. So F indicates liquid, HFG at HF at point D, HF at point D. So at point D pressure is 0.04 bar. So HF at 0.4 bar, HF at 0.4 bar is 121.44. So 121.44 at 0.04 bar. At 0.04 bar HF is 121.44. So here it is 121.44 kilojoules per kg. So enthalpy at point D is also known to us now. So now to find out enthalpy at point E, we must know enthalpy at point E. Find out enthalpy at point E, we must know HD and pump work. So HD is known to us. Now yet to find out HE, if we know HB is known, if we know HE, we can find out heat supplied. So pump work is required. So pump work formula is known. So now our duty is to find out pump work. Once we know pump work, then we can find out HE. If we know HE, we can find out heat supplied. That is denominator of this equation. So here pump work is equal to specific volume of condensate into P1 minus P2 into 10 to the power of 5 divided by 1000. So this will be in kilojoules per kg. So VW, specific volume at point D, pressure at point D is 0.04. So this is 0.001004. 0.001004 is specific volume. Pressure is increased from P2 to P1. P1 pressure is 30 minus 0.04 into 10 to the power of 5 divided by 1000. On simplification, this gives us 30 minus 0.04 into 100 to 0.001004. So this will be, pump work is 3.007 kilojoules per kg. This is how we got pump work. So now once we know pump work, we can see here, once we know pump work, we know HD, we can find out HE. Once we know HE, we can find out heat supplied. So HE, enthalpy at point E, enthalpy at point E is equal to HE is given by HD plus of pump work. HD is known, enthalpy at point D is known as 121.44. This we have calculated. Also we have calculated pump work as 3.007. So enthalpy at point E, HE, is equal to plus of 121.44. So this gives us 124.44 kilojoules per kg is the enthalpy at point E. Now heat supplied can be obtained from this. Heat supplied is equal to HB minus of HE. So heat supply starts at point E. From E to A, sensible heat is supplied. A to B, here latent heat of vaporization is supplied. Enthalpy at point B minus enthalpy at E gives us heat supplied from point E to B. The enthalpy at point B is known, that is 2802.51, minus enthalpy at point E is known, 124.44. So this gives us heat supplied per kg, 2802.51 minus 124.44. This is 2678.07 kilojoules per kg of heat is supplied. So denominator of efficiency equation is ready now. So denominator can be known. Now to find out the efficiency of cycle, we must know numerator. So what is in the numerator? Turbine work minus pump work. Pump work is known. Now turbine work we have to find out. So to find out turbine work, HB is known. HC we have to find out. To find out enthalpy at point C, we must know dryness fraction at point C. So this process B to C is constant entropy process. Entropy at point B is equal to entropy at point C. So from that equation, entropy at point B is equal to entropy at point C, we can find out dryness fraction at point C. So using this equation, we can find out enthalpy at point C. Once we know enthalpy at point C, we can find out turbine work, then we can find out net work. So to find out dryness fraction at point C, why to find out dryness at point C? To find out enthalpy at point C, we must know dryness fraction. To find out dryness fraction at point C, we must equate entropy at point B is equal to entropy at point C. So here, once again, I will draw here the diagram. point A, B, C, D and E. PS diagram. So now entropy at point B is equal to entropy at point C. To find out entropy at point C, entropy at point B is equal to entropy at point C. So condition of steam at point B is it is dry saturated steam. At point C it is wet steam. So to find out entropy at point B, we can write as SFB plus of SFG at point B is equal to SF at point C plus XC into SFG at point C. So at point B, at pressure B, we can find out SF and SFG. So pressure at point B is 30 bar and here it is 0.04 bar. So properties at SFB and SFG are at pressure 30 bar. So taking it from steam table, at 30 bar it is 2.6456 SFB is 2.64 because pressure is 30 bar. So at point B 2.6456 plus of SFG 3.5412 3.5412 is equal to SFC. At point C pressure is 0.4 bar. So at pressure 0.4 bar SF is 0.4226 0.4226 plus XC into SFG at C is 8.0520 8.0520. So on simplification we get dryness fraction as 0.95. Once we know dryness fraction at point C, the enthalpy at point C can be obtained as HF at point C plus XC into HFG at point C. So HFC at point C, enthalpy at point C, enthalpy of liquid at point C at 0.404 bar it is 121.44 121.44 plus XC is 0.95. HFGC at 0.04 bar it is 2432 into 2432.95. On simplification, the enthalpy at point C can be obtained as 1863 1863.4 kilojoules per kg. So once we know HC, we can find out turbine work done by turbine. WT work done, WT is equal to HB minus of HC. HB value already we have calculated. Enthalpy at point B is 2802.51 2802.51 minus HC is 1863.4. On subtraction, the turbine work will be approximately equal to 940 kilojoules per kg. Turbine work is known, net work can be obtained. Now net work is equal to turbine work minus pump work. Turbine work is 940 minus pump work, just we have calculated as pump work is 3.007. So here we have calculated here 3.007. 3.007 means 3 approximately. So this will be 937 kilojoules per kg. So now efficiency can be obtained. Efficiency of Rankine cycle. The efficiency is equal to net work divided by heat supplied into 100. Net work is known to us, that is 937 divided by heat supplied. If we see, heat supplied is 2678. 2678.07 into 100. On calculation will be 35%. Approximately this works out to be 35%. Now next thing, he has asked us work ratio. So what this work ratio is? So it is the ratio of net work divided by turbine work. Net work is 937. Net work is 937. 937. Then turbine work that we obtained is 940. 940. This work ratio is approximately 0.997. Then specific steam consumption. Specific steam consumption is equal to 1 divided by network WN into 3600. So 3600. Network is 937. This gives us 3.84 of steam in kg per kilowatt hour is consumed. So how much of steam is required per kilowatt hour is calculated with the help of this equation. So this is how the problem of Rankine cycle is obtained systematically. So what we have to do is we have to write down the equations, what we have to find out, and then we have to start from bottom and coming back to final net work done and efficiency. So this is the efficiency is a major parameter which is asked. So to find out efficiency we must know net work done and heat supply. So to find out various properties in this Rankine cycle we have to use steam table, and by using steam table we can find out properties of steam, and those properties are used to simplify this problem. Thank you.